Good. Okay, so today, first I want to correct the calculation we did last time. So I had that error about the 4 versus 1/4 in the sliding ladder because I was trying to think on my feet. And so I worked it out, and the answer we get by using the sort of trig approach that you suggested agrees with what you get by doing Pythagoras, which is the way I solved it, as it must. If math works, the two should agree. So I just want to walk through that and convince you that things work when you do arithmetic correctly. So that'll be one thing. And then we should prove L'Hopital's rule, which we introduced last time. This kind of surprising result that if you take a limit of a quotient and the top and bottom both go to 0, then in many cases, subject to some assumptions, the limit is equal to the limit of the quotient of the derivatives. So that's pretty powerful. We'll go through a couple examples. And then that's kind of the last major, content-related thing, the last topic in applications of derivatives. So then I just want to go through a bunch of problems. We'll probably spend a couple sessions on this. Today I want to do more problems related to physics, in particular projectile motion, which you will do on CD4 in greater detail. And that'll probably take, the second half of the meeting since it's rather involved, but you can treat it as an extended example. So thoughts or questions about the plan?
I have no questions.
Cool. Okay. Good. So first back to the ladder. So to remind us of the problem statement, we had this thing last time about this 10-foot ladder. So the hypotenuse of this triangle has a fixed length of 10 feet. It rests against a wall and it's starting to slide down the wall. So this point is moving to the left and this contact point is moving downwards as it slides down. And as you suggested, we can do this sort of differentiation procedure to the angle theta that the ladder makes with the ground. So the question we're trying to solve is when the ladder forms a 60-degree angle with the ground, so when theta is 60 degrees, how fast is the top of the ladder sliding downwards? So I believe the variables you used last time were to assign this height to be, I think, h of t, and to assign this length along the horizontal to be L of t. So we have these two, and then the relationship between them and theta is that the tangent of the angle theta, which also depends on time, so tangent of theta of t, is going to be the opposite h of t over the adjacent L of t. And our strategy last time was to differentiate both sides of this equation, which I'll show on the next slide, and then we saw that that involved both theta dot, h dot, and L dot. So we wrote down a second equation in order to eliminate one of those variables. I think we also wrote down cosine of theta of t is going to be the adjacent L of t over the hypotenuse, which is constant, this fixed 10 feet. So I think the strategy of our solution last time was to write down these two equations, differentiate them, and then try to find the rate of change of the height, so h dot of t, at the time when there's this 60-degree angle. So that was our strategy. The actual calculation, well, I guess I should erase some of this, but let's see. So as I said, h of t and L of t are as in the diagram. We write down the tangent and the cosine, take the derivatives, as you reminded me and I misremembered, the derivative of tangent is secant squared. So by the chain rule, d dt of tan theta is secant squared theta theta dot. So you get this guy on the left. By the quotient rule on the right, you get this thing, h dot L minus L dot H over L squared. You differentiate the second equation with the cosine, which gives you a minus sine theta theta dot, which is L dot over 10 feet, because this is a constant. And then the only challenge remaining is to find all of these quantities, what they're equal to at the time when theta equals 60 degrees. So to do that, we made this argument about, I guess, a 60, 30, 90 triangle, which we know has, fixed ratios between these sides. There's this, how does it work? L, well, I shouldn't use the same variable L. Let's call this A, 2A, and a root 3, if I remember correctly how this works. So at the time in question, since we know the hypotenuse is always 10 feet, so 2a is 10 feet, then that means that a is 5 feet dividing by 2, and this thing, a root 3, is 5 root 3 feet. So, damn it. So we used that last time to find the values of h and L at the time in question. And then you can plug those into these two equations. So I've skipped a couple of steps in this slide, but I think I can hopefully do the arithmetic on the fly. What I did was first take the top equation and multiply both sides by L, right? So if you have L squared on the left, you cancel an L squared on the bottom of the right side. Then you add L dot H to both sides, right? So that eliminates this thing. And then I just reversed the order, so I wrote the right side as the left side. And after doing that, you have H dot L, so this is H dot L, which is H dot times 5 feet, since I've argued that L, the horizontal distance, is 5 feet at the time in question. So this is H dot L. And on the right side, I've written what is the left up here. So there's two pieces. First is the L squared secant squared theta theta dot. So again, L is 5 feet, so here's the L squared. The secant squared theta, which is where we made, I mean, it was me, I just derped. Where I made the error last time was in writing down the value of secant squared of theta, since we know that secant is 1 over cosine. Cosine of 60 degrees is a half. So 1 over 1/2 squared is 1 over a fourth, and 1 over a fourth is 4. So this should be 4 and not 1/4, as I wrote last time. And then this bit is the theta dot. So how do we get the theta dot? Well, we get the theta dot by solving the second equation for theta dot. So this thing means theta dot equals minus L dot over sine theta times 10 feet. So I plug that in for theta dot in the first equation. So here's the minus sign, then L dot. We're told in the problem statement that this is a time at which the bottom, the bottom rung of the ladder, this thing is sliding away at the rate of 1 inch per second. So that's the L dot. This whole thing's theta dot. So L dot in the top, 10 feet. Sine theta, well, we know sine 60 is root 3 over 2. So we drop that in the denominator. The second piece is this L dot H guy. So again, at the time in question, we know L dot is an inch per second, and we know H from the diagram is this thing, which is 5 root 3. So I put in L dot times 5 root 3. And at this point, all we have to do is some unit conversions and some algebra, or not algebra, really arithmetic, I guess. So I will try to do this. Let me erase everything so we can just focus on the arithmetic. We're trying to solve this top equation for H dot. So the first thing I do is cancel the factors of 5 feet. So there's a 5 feet here, here, and here. So I cancel one, that leaves a 5 feet left when we cancel one factor in the square. Cancel a 5 here. Another problem is the different units. So there's feet in some places and inches in other places. So I will convert all of the feet to inches by multiplying by 12. And doing that, we get H dot equals, well, let's see, what's 5 feet in inches? 5 times 12 is 60. So 60 inches times the 4 stays times the minus 1 inch per second all over what's 10 feet in inches. That's 120 inches. We still have the root 3 over 2. In the second term, we get 1 inch per second times root 3 feet. Again, multiply by 12 to go to inches. So this should be 1 inch per second times 12 root 3 inches, I believe. Wait, sorry. No factor of feet. Sorry, that's wrong. We canceled the factor of 5 feet everywhere. So when you cancel the number, you cancel the unit as well. So 5 feet cancels here, 5 feet cancels here. On this side, we cancel both the number 5 and the unit feet. So I was lying. There's not a 12 here. there's no need to convert feet to inches because the factor of feet has been canceled. You treat the letters ft just like a variable. You cancel those. Good. Okay, so we have this. Then we just need to simplify. How do we simplify here? Well, let's see. We have in the denominator 120 times root 3 over 2, so we can cancel a 2 and replace that 120 by a 60. Then I should use a different color. We cancel the 60. 60 inches cancels with the 60 inches outside, right? So, well, this is bad flow, bad direction, but I'm going up in equations now. So after canceling the 60 inches top and bottom, we have a 4, a 1 inch per second with a minus sign, and a root 3. So this is minus 4 inches per second over root 3 plus, I'm going to multiply this by 1. I'm going to multiply by 1 in a clever way, which is the following. I multiply this by root 3 over root 3. I'm getting a common denominator, right? So I want to combine these two. So when I multiply by root 3 over root 3, in the top I get root 3 times root 3, which is 3. In the bottom it's just root 3. And the units are inches per second, which is good. You should always check that you're adding together quantities with the same units. So then we're in good shape, because we combine the numerators. Minus 4 plus 3 is minus 1. So we have a minus 1 over root 3, and the units are inches per second. So in fact, this is the correct answer. Minus 1 over root 3 inches per second. And this makes sense from an answer analysis perspective because the sign is negative, so the height of the ladder is decreasing, right? It's moving downwards, which is good. Last time we had a positive answer, which is bad. Okay, so in the next slide I will compare this to the solution with Pythagoras, but before doing that, thoughts or questions on this solution?
I muted myself and thought I still had push to talk on.
Bad
I don't know anymore. I have no questions.
Okay, so you're happy with this. You agree that all of the manipulations were correct this time, at least?
Yes.
Good, okay. So we should do a check, a sanity check, that this matches the other solution I wrote using Pythagoras. So if you, instead of using trigonometry, if you just said, well, I know how triangles work, if, instead of L and H, we call these X and Y, and you use the Pythagorean theorem, and argue that x squared plus y squared must be the hypotenuse squared, so 10 squared is 100, and you get 100 feet squared. Differentiate both sides. This gives you 2x x dot plus 2y y dot equals 0. Or, in other words, solving for well, I won't do that. So the 2's cancel. We plug in x and y at the time of interest, which I drew for you on the previous slide. So there's a 5 feet and a 5 root 3 feet. And then you convert feet to inches. So again, canceling the 2's. This x being 5 feet gives us 5 times 12 is 60 inches. We are told that x dot is an inch per second. Y again is 5 times 12 is 60 times root 3 is 60 root 3 inches times y dot. And then you just divide both sides. You move this to the other side and then divide by the 60 root 3. And the 60's also cancel. And we're left with minus 1 over root 3. So this is good. I mean, it's always a value add if you can solve a problem in 2 ways and make sure the answers agree, because it will help convince you that you haven't made a mistake. So this is good. Okay, that's just errata from last time. Thoughts or questions before we go on to L'Hopital's rule?
It would seem that the by Pythagoras was a lot quicker.
Yes. This is a common theme, I think, in real problems and also in my life personally, is that when you start trying to solve a problem in a particular way and it becomes very hard, you never know, should I continue solving the problem this way, or should I give up and try something else? Because it's very hard to judge, how close am I to the solution? So would it be faster just to, press on and continue working with this approach, or would it be faster to give up and use a different approach? And that's something that it's hard, but it develops over time with experience and taste, I think. So I don't know. I mean, when we were solving it last time, I got kind of nervous partway through because I'm not very good at thinking on my feet, and I was trying to just work through this solution in real time. And as you saw, I fucked it up. But I think it was worth doing just to illustrate this difference that sometimes just very reasonable and comparable sounding starting points, use trigonometry versus using Pythagoras, they both sound perfectly reasonable, but they lead to very different, degrees of difficulty in the solution. So, I don't know. I'm not saying anything meaningful. I'm just kind of rambling, but it's an interesting observation, I think. Other thoughts?
I have no further thoughts.
Okay, so let's go back to L'Hopital. So I've repeated the theorem from last time. Last time I think we stated but did not prove the theorem. So the idea of this theorem is that under pretty mild assumptions that the limits for f and g at x goes to a both exist, and the limit of the quotient of their derivatives also exists. These are very mild assumptions. If that's true, then the limit of their quotient is the same as the limit of the quotient of their derivatives. So this is, I think, surprising and also quite powerful. I've used this actually in research problems. So in like the physics stuff I'm working on with Saab, this has come up. Sometimes I need to actually use this result. So it's rather powerful. And to prove this rigorously, we're going to need to use another result which we actually did prove last time, the Cauchy mean value theorem. And I'm just repeating this here to remind us. So the Cauchy mean value theorem tells us this thing about two functions f and g. If they're continuous on a closed interval and differentiable on the associated open interval, then there must be some number x on that interval where this equation is true. So f of b minus f of a quantity times g prime equals g of b minus g of a quantity f prime. The reason we call this a mean value theorem is that if you choose g of x equals x, then this thing reduces to the usual mean value theorem because g prime is 1. So this is telling us f of b minus f of a equals, well, that's just b minus a f prime of x, and when you divide both sides by b minus a, you see this is the usual mean value theorem, that there exists one number x where the tangent line slope f prime at x is the same as the secant line slope f of b minus f of a over b minus a. So this is more powerful. This strictly implies the usual mean value theorem, but it's also, it implies other results as well if you pick a different choice of the function g. Okay, so that's what we're going to try to prove this time in Act 1. We're going to prove the thing on the top half, L'Hopital's rule. But the proof is kind of a bitch, so before proving it rigorously, I want to do some exploration in the form of a challenge. So let's just try to convince ourselves for why this might be reasonable. Why would it make sense that the limit of a quotient might be the same as the limit of the quotient of the derivatives? So I'll ask you to walk me through it. Let's give a quick and dirty argument, so you don't need to prove anything or be rigorous, and you can, be hand-wavy or sloppy. But I will ask you, tell me why this might make sense by using a tangent line approximation in the numerator and denominator. So walk me through. Start with this limit. The limit as x goes to a of f over g. Do a tangent line approximation top and bottom, and then explain what happens afterwards. Do you have push to talk on, or are you thinking?
I do not have push to talk on.
Okay, good.
So it would seem that you suggest simply taking the approximation of f of x on its own. So
Well, I think we should do both. So you should tangent line approximate both f and
Well,
g.
yeah.
But yeah, that's
So
good.
f the tangent line approximation applied to f of x is get us just really trying to remember f of a plus thinking. I don't know if f of a is quite right.
Well, that's the first piece, right? So the tangent line approximation has the constant, which is the point about which you're expanding, and then it has the slope and the distance between the point you're evaluating at and the point where you're expanding about, right? So there's an f
Yeah.
of a, and then what's the slope piece?
F of a plus f prime of x times say. Oh, okay.
Yeah. Always remember this. This is very important. This is the reason why the tangent line approximation is good. You don't need to know the derivative at x. You only need to know the derivative at a, right? So that's important. Good. Okay, so what do I do for g of a then?
Identically, it's going to be g of a plus g prime of a times x of a. I mean x minus a.
Good. Okay. So let's remind ourselves of the hypothesis of L'Hopital's rule. So we're assuming that the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is also 0. So we can be a little sloppy here because we're just doing exploration. We're going to say, all right, I don't give a fuck about pathological cases. All functions are continuous. Everything's smooth. I don't care. So if the limit as x goes to a of f is 0, and the limit as x goes to a of g is 0, and we assume they're continuous, I think that should mean f of a is 0 and g of a is 0, right? So if we're being sloppy and say that, what does this thing on the right side simplify to?
Muted myself for some reason. I believe that we can split this into two. Wait, did you say f prime of a equals 0 or f of a equals 0? F of a equals 0. I answered that both. Right.
Why is my pen being screwy? But yeah, the claim was that damn it. The claim was that the limit as x goes to a of f of x equals 0, so let's just assume I don't know how to write it. Assume f of a, damn it. Quiet Slack. Okay, yeah, so assume
He
f
says
of a
infinite breadsticks.
That's important. Okay, yeah, so if f of a and g of a are 0, then what happens?
I believe that we should split this into two fractions.
Well, do we really need to split it if this thing is 0 and this thing is 0? There's no
We
splitting.
just insert it equaling 0. Oh my god.
Yeah, we're being sloppy. No reason to worry too much for the exploration. So, okay, so what happens if we set both of those to 0?
We end up with just f prime of a times x minus a over g prime of a times x minus a. You can divide the x minus a out since we are assuming x not equal to a in the definition of limit.
Good, that's important. So the limit is totally insensitive to what happens at x equals a. So this is not 0, and we can divide. And then, indeed, we get what was promised by L'Hopital's rule, that the limit of the quotient f over g is the same as the limit of the quotient f prime over g prime. So this was very sloppy. I'll highlight why this isn't actually proof in a moment, but this is kind of intuitively why, if you're just doing some exploration and trying to convince yourself that this might be true, why you might think that that is the case. So good. Thoughts on this?
I have no thoughts.
Okie dokie. Okay, so good. As you say, if we assume both f and g are C1, right, so they're both continuously differentiable, which we didn't actually assume in the statement of L'Hopital's rule, but whatever, we're just exploring. So if you assume that's true, here's the sketchy step. The tangent line approximation is an approximation. So what does it mean for this limit to be approximately equal to this other limit? I haven't really defined that in a satisfactory way, but if you're willing to brush that under the rug, then as you've told me, you can set these to 0, you can cancel, and argue that this should be the same as the limit of the quotient of the derivatives. So actually this step about approximately equal to within a limit, so this can be made rigorous. We could actually argue that in the limit as x goes to a, the tangent line approximation becomes exact, and we could bound the error, and we could turn this into a proof. But I don't actually want to do that, because the assumptions are too strong. In this exploration, we're assuming that f and g are both continuously differentiable, and as you notice perhaps in the statement of L'Hopital's rule, we're not actually assuming anywhere that f and g are C1. We just assume that the limit of the quotient of their derivatives exist. So this is much weaker than the C1 assumption. So I don't want to turn the exploration into a proof because it assumes too much. You always try to prove theorems using the weakest possible assumptions. Assume as little as possible and try to get, the strongest possible results. But okay, so with that said, I guess we should move on and actually prove it rigorously now, although it's kind of a bitch. So anyway, that was the exploration. Let's do the real proof. So there's going to be 3 slides. It's kind of hard because if we're proving equality of 2 limits, really unless we use an intermediate result like the squeeze theorem or our theorems about continuity of polynomials, there's only one way to do it, which is to fall back on epsilon deltas. So this is one of those examples where you're trying to build something new, and you have to kind of go back to the source code, the epsilon deltas, and build it from scratch. So anyway, enough preamble. Let's actually do that. First, I want to highlight the assumptions we made. So I've asked you to assume that the limit as x goes to a of f prime over g prime exists. So if that exists, then certainly that means that the derivatives must be defined near a. Right? If this limit exists, then the quotient of these, the numerator and denominator should also exist. So more formally, that means that there must be some interval, so there must be a number delta, so you can pick an open interval from a minus delta to a plus delta, and on that interval, both f prime and g prime are defined at all points on the interval except possibly x equals a, where I say, we exclude x equals a because, as you noted, limits are insensitive to the behavior of the function at the point in question. So there's an interval where the derivatives exist. That's the first assumption. Second, if this limit exists, that means the denominator must be non-zero on some interval near a. So we must have g prime not equal to 0 for all x in that same interval. Again, except possibly at the point in question, x equals a. So those are 2 things which follow from our assumptions. Now here's an argument, a sort of without loss of generality argument, because in the statement of the theorem, nowhere did we assume that f and g are continuous or even defined at a. So they could be undefined, they could be discontinuous, whatever. So I'm going to argue that without loss of generality, we can actually assume that they are continuous at a. And the reason for that is the following. If they are not continuous at a, then we define new functions which are the same as the old functions except at a single point. So we define a function f hat of x, which is almost everywhere the same as f of x. So this guy f hat agrees with f of x everywhere where x is not equal to a, and then I just put in by hand. I say I demand that f hat is 0 when x equals a. And same thing with g hat. You just say g hat, he's basically the same as g, except I insist that g hat is 0 at x equals a. So it's a redefinition at a single point. Now, we could run the remainder of this argument, the proof in the next 2 slides. We could run that entire argument on f hat and g hat instead of on f and g, if we wanted. So the claim is that if these guys are discontinuous at A, just replace them by f hat and g hat, run the remainder of the argument on f hat and g hat, and that will give you the same answer. That's the point. So for now, we can assume that these guys are continuous because f hat and g hat are continuous. Why are f hat and g hat continuous? Well, we assumed in the statement of the theorem way back here that the limit as x goes to a of f is 0, and the limit as x goes to a of g is 0. So if we define these functions that are equal to 0 at a, then clearly the limiting value equals the function value, right? The limits are equal to the function value, which means they're continuous. So that's the first ingredient, I guess, the assumption that these guys are continuous. Okay, so once we have that, now we need to do some other housekeeping. So we're trying to prove that this limit equals the limit as x goes to a of f over g. That's what we want. I should put an exclamation point for want. So if we want to show that these two limits are equal, we should first argue that g is not 0 on the interval. So we would have a problem if g hit 0 somewhere on this interval, because then it's not very convincing that the limits could be equal, because this limit blows up at some points. So first I will argue that g is non-zero on this interval, the delta interval. So to argue that, you pick a point x, so fix x in this interval from a to a plus delta. And now we suppose by way of contradiction that g of x equals 0 on this interval. So we assume g of x equals 0 and apply the mean value theorem. Why can we apply the mean value theorem? Because I've argued that we can assume g is continuous based on this argument here without loss of generality. So g is continuous on this guy, he's differentiable on this guy, as we've said. So by the mean value theorem, if g of x were equal to 0, then we would have a point in the interval, maybe I'll call it c. By the mean value theorem, there must be a point c in the interval where the tangent line slope equals the secant line slope. The secant line slope is g of a, well, sorry, I guess we're calling this x, right? G of x minus g of a over x minus a. Right, so this thing, by the mean value theorem, must be true at some point c, but g of x, by our assumption, we assumed by way of contradiction that g of x is 0, so this is supposed to be 0. G of a, based on this hat argument, we can assume that this guy's continuous, so g of a is 0, so the right side is 0. So the punchline is, if we assume by way of contradiction that g hits 0 at some point, by the mean value theorem we find there must be another point where g prime is 0, but that contradicts this thing. Right? From the statement of the theorem, we know g prime is non-zero on the interval. So, okay, that's the first part of the proof, is just this housekeeping, making sure that the statement itself is sensible. So thoughts or questions on the first slide of the proof?
I do not have any thoughts or questions. It is understandable for now.
Okay, good. Okay, so let's move on. So now the real ingredient, now that the housekeeping has been done, the real player in this proof is the Cauchy mean value theorem. So let's just remind ourselves, the Cauchy mean value theorem tells us that there must be a point x where this equation holds, given two functions f and g, continuous and differentiable on the appropriate intervals. So let's apply that Cauchy mean value theorem to the functions f and g that appear in this quotient, right? The f divided by g. So just copying the statement of the Cauchy mean value theorem, well, we know without loss of generality that f of a is 0. We know g of a is 0, so I'm putting those in. But the Cauchy mean value theorem guarantees that there exists some number which I'm going to call alpha x, alpha sub x, because this depends on the interval that we've fixed from a to x. So this is what I was calling c before. But anyway, so it tells us there exists a number alpha sub x with the property that f of x times g prime at alpha sub x is the same as g of x times f prime at alpha sub x. It's just the statement of the Cauchy mean value theorem. So this is great because by algebra, now we can just divide and find that this equation implies, dividing by g, f over g is the same as f prime at alpha sub x over g prime at alpha sub x. So this is almost what we want, right? We can take the limit as x goes to a, roughly speaking, we can take the limit of both sides of this equation, and that's almost what we're trying to prove. But there's a few, being methodical, there's a few things to check that it actually makes sense to take this limit of both sides of the equation, because we really want this to be the same as the limit as x goes to a of f prime of x over g prime of x. So it's not totally clear at the moment that this limit in the middle is the same as the limit on the right. We have to prove that. To do that, we need a couple steps. So first, this alpha sub x, I claim that as x goes to a, alpha sub x approaches a. So maybe that's pretty obvious, because this alpha sub x sits in an interval between between a and x. So as x goes to a, this interval gets smaller and smaller, right? The limit as x goes to a of this interval shrinks down to just the point a. So roughly speaking, there's no room in the interval from a to x. As x goes to a, there's no room for this guy to approach any other point, right? The only point that stays in that interval is a itself. But we should actually prove that. So here's the proof. It's very simple. Let epsilon greater than 0 be given. You just pick delta to be the same as that epsilon, so delta equals epsilon. Alpha x by construction lies in the interval from a to x. So if 0 is less than the absolute value of x minus a is less than delta, which is just the statement that this x is within distance delta of a, so the interval from a to x has distance, or total measure, if you will, less than delta. So if this thing is true, then by definition, alpha x lies in the interval from a to a plus x, which is, from a to x, which is the same as the interval from a to a plus delta, based on this assumption here. But delta equals epsilon, so alpha x lies in a to a plus epsilon, open interval, and that means that the absolute value of the difference, alpha x minus a, is also less than epsilon. Just by looking at this. This guy sits in an interval, and by the definition of interval, that's true. So that's the first thing. The limit as x goes to a of alpha sub x is a. Kind of obvious geometric reasoning. Thoughts on this?
I don't miss delta epsilon.
Yeah, I get that reaction a lot. I actually think it's very elegant. I mean, you probably don't think it upon seeing your first exposure to delta epsilon stuff, but it is, I mean, hopefully you at least appreciate, even if you don't like it, that it was necessary and that everything we've done since has been built on it.
Yes, definitely.
Good. Other thoughts?
Sudden random. You had mentioned that at some point we're going to be talking about x as it goes, well, the limit as something goes to infinity.
Yes.
When was that again?
I'm not sure when to do that. I dislike the organization of the AOPS book because they talk about limits at infinity in this chapter 6 or 7, I think it is, this random collection of unrelated topics. So I'm not sure if we should do that this chapter. I guess we have a few sessions left. I usually do like 10 sessions per chapter. So we could spend a few more sessions talking about limits at infinity in this chapter, or we could postpone it and then do it after integration and talk about limits at infinity. I don't know which is better. Do you have a preference?
I have no preference.
Okay, well, good. Putting the onus on me to decide then. Yeah, I don't know. I'll think about it. I think they're interesting. They come up in computer science a lot, as I told you, because you care about, say, the asymptotic growth of how much... My pen's fucked again. we talked about this big O notation, right? So how long it takes your program to run as the input gets big. So, well, I can't write, but anyway, so that naturally involves a limit at infinity. So it's quite important, but I don't know kind of pedagogically where it should fit in the set of chapters. So I don't know. We'll see. Good. Last part of the proof. So we know that thing. The last thing we have to prove is that these limits are equal. Because if these limits are equal, then we're in good shape, because we proved that the limit of the quotient is the limit of this weird quotient of derivatives at alpha. So if we can prove that that weird quotient at alpha is the same as the quotient of the usual derivatives, then we're in good shape, because we proved, the limit of f over g is the limit of f prime over g prime, which is what we want. So, okay, this, I almost want to argue, I want to just kind of wave my hands and say we proved this thing back in chapter 2 about the limit of a composite of functions, and just kind of skip the details, but I should be honest, we can't actually apply that here, because the hypotheses don't apply. When you proved that thing about the limit of a composite, it assumed that the outer function in the composite was continuous, and we haven't actually assumed that this quotient is continuous, so we can't use that result. We actually have to prove it from scratch. So here's me attempting to prove it from scratch. I hope this is right. I looked up the proof in Spivak, and he left this step as an exercise for the reader. So I had to think about this, and hopefully I think I got it right, but we'll see. So here's the proof that these limits are equal. So again, we fix an epsilon, let epsilon be given. We've assumed that this on the right side exists in the theorem statement, so let's call the value of that limit L. So if that limit exists by the epsilon delta definition, we can find a number delta 1, so that whenever y is within distance delta 1 of a, then the output f prime of y over g prime of y is within distance epsilon of L. So pick such a delta 1. That's the first thing. Second thing, we proved on the previous slide that as x goes to a, alpha x tends to a. So if this limit exists, again by the epsilon delta definition, there exists some number delta 2 with the property that whenever x is within distance delta 2 of a, then alpha sub x is within distance delta 1 of a itself. So just to be totally clear, my pen's skipping, but we are using the delta 1 of the first step as the epsilon in the second step, right? Normally you say the output is within distance epsilon of the limiting value, but the epsilon we're using here is the delta 1 of the first step. So we're kind of chaining together our delta epsilon arguments. Okay, so if you do that chain, here's the proof that these limits are equal. So I have to show that the output of the left side is within distance epsilon of L, if they're equal. So I claim that if you hand me an epsilon, I hand you this value delta 2, and then whenever x is within distance delta 2 of a, by the first step, when x is within distance delta 2 of a, then alpha sub x is within distance delta 1 of a, and then we apply the first result with y equals alpha sub x, because we know alpha sub x is within distance delta 1 of a, which is exactly what we need in the first step, right? This tells you that if the thing is within distance delta 1 of a, then this will be true. And the second thing tells us that the thing, here alpha x, will be within distance delta 1 of a. So the assumptions are precisely what we need. So combining those two implications, whenever x is within distance delta 2 of a, this is true, so this is true, so the limit of the quotient is within distance epsilon of L, right? So that's good, because that's what we wanted to show. If the limit of the quotient of the derivatives at alpha is within distance epsilon of L for any epsilon, that's by definition the statement that the limit of this weird quotient at alphas is equal to L, which is just what we called the limit of the ordinary quotient of derivatives. So now we're done. Now we've proved that these things are equal. You combine that with the result in the previous slide that we showed that the limit of the quotient with no derivatives equals the thing with the alphas. So if this limit equals this limit, and this limit equals that limit, then by the transitive property of equality, that limit equals that limit, which is what we wanted to show. So it's kind of a pain. We had to do some bit fucking, but I think it's useful to go through and see why it works. Questions or thoughts on this proof? I think you muted yourself.
Oh, yes, I did. Whoops.
I'm assuming that's a no thoughts then.
That is correct.
Okay, good.
I wasn't thinking.
That's fine. I mean, it's kind of hard to follow, so it's a lot to take in. But anyway, so if we're convinced it's true, let's use it in an example. So this is an example we would not have been able to evaluate before having this theorem. So what is the limit as x goes to 0 of the quotient x divided by the tangent of x?
Here I go muting myself. I don't know why I keep doing that.
Lol.
Okay, yeah, I'm very tired. Anyways, we are going to take the derivative just to have an idea of what this is going to be.
Okay, so good. What do we get?
Top is equal to 1 and the bottom is equal to thinking secant squared x?
Yeah.
Was it?
We had this for the ladder.
Yup.
Okay, so you say I differentiate top and bottom because first we should check that L'Hopital's rule only works if top and bottom both go to 0, right? So, but clearly as x goes to 0, x goes to 0, because I've just said the same thing twice. Tangent to sine over cosine, sine of 0 is 0, so top and bottom go to 0. That's good. So then, as you say, we can take the derivative of the top and bottom, limit x goes to 0, 1 over secant squared x. And then what's this?
For whatever reason, I muted myself. Trying to remember. We see by that secant is 1 over cosine, and in this case, secant squared is equal to sine, as actually is equal to 1.
Good, yeah, because secant's 1 over cosine,
Yeah,
cosine
okay.
is 1. Good.
So there's going to be 1 over 0,
No,
but 0 brought to the top. What?
no, you just told me this is 1 over...
Cosine squared.
Yeah, so secant squared is 1 over cosine squared, and we know cosine of 0 is 1. Right?
Oh.
It's
And, yep.
unit circle. This is, I don't know why I'm pen skipping, but angle 0, this is pretty clearly 1, right?
Okay.
Good.
One of these days I'll remember correctly.
It's like, I like the alphabetical argument, like that C comes before S, and X comes before Y, so cosine goes with X, and sine goes with Y. I don't know, kind of stupid. You said you couldn't sleep until 5 a.m. When did you wake up?
Good question. I think like 7:45.
Doing pretty good for less than 3 hours of sleep. Okay, good indeed. So by L'Hopital, this is the limit as x goes to 0 of 1 over secant squared, which is indeed 1. Good. So a slightly more theoretical problem. We'll do a proof. Suppose that we have some function f. I hand you an f. He's continuous at a. His derivative f prime exists everywhere in some interval containing a, except possibly at a. So the derivative, it's nice and exists in an interval, and you assume that the limit as x goes to a of f prime exists. We'd like to prove that f prime at a also exists. So just because the limit exists doesn't mean the function value exists. As we've seen, you can have point discontinuities. But we'd like to prove that f prime exists at a, and that the derivative is continuous at a. So in other words, the limit as x goes to a of f prime is equal to the value at f prime. So first, before even trying to prove this, this sounds almost obvious. What would it look like if this were not true? So for instance, if the derivative, damn, that's annoying, it's Skippy pen. So I'm going to graph the derivative f prime. How could this theorem not be true? Well, if f prime is defined everywhere in an interval around a, but he had a point discontinuity, so maybe the derivative, is supposed to be up here, but he has a point discontinuity, and he spits out this value down here. If that were true, then the theorem would be false, right? This would say the derivative exists, so f prime exists in an interval around a, and clearly the limit as x goes to a of f prime exists, right? Because he approaches this point up here. But that point which he approaches in the picture I've drawn is not the same as the actual function output, which is down here, because he has a point discontinuity. So the statement of this theorem is simply that, if you have a continuous function, the derivative exists on an interval, you can't have a point discontinuity in the derivative. This can't happen. And if you think about it for a moment, that kind of makes sense geometrically if you just think about what it would have to look like for the original undifferentiated function if this were true, right? So what would it look like for the original undifferentiated function if the derivative had a point discontinuity, right? It would be like this. So here's f, he has a, I don't know, maybe negative slope here, so he's decreasing, and then he's increasing, and then right at a, instead of having the slope that he's supposed to have, he has a much smaller slope, so he gets less steep here. So he kind of discontinuously jumps to having a really unsteep slope when he should have a steep slope. So he looks like this somehow close to a, but only really at the point a, and then somehow goes back to what he was doing before. See, that doesn't really make sense, because you can't discontinuously jump to having a different slope at a, because the concept of slope necessarily requires you to compare the value of the function at two nearby points, right? So if he suddenly jumps to having a very unsteep slope near a, he has to do that not just at a, but at least a very small interval around a, right? Because to have a slope, you have to compare 2 points and do a rise over run, roughly speaking. So anyway, the reason this theorem is true, that derivatives under these assumptions cannot have point discontinuities, is mostly just because of this geometrical reasoning, that you cannot discontinuously jump to have a different slope at a single point, because slope at a point is kind of a tricky thing to define. But okay, well, fine. That's just intuition. How do we prove this? So I've given you a hint. Define these new functions, write down the definition of the derivative in terms of those functions. We'll use a slightly different definition than the usual one, but we've proven that this definition we'll use here is equal or equivalent to the usual definition, and then I'll ask you to apply L'Hopital's rule to that expression for f prime. So, okay, what do you think we should do?
Well, you should follow the hint exactly.
Okay.
Thinking we define a function h of x equal to f.
Good. Not going to rewrite that. But yeah, suppose
we have those. We can move our f of x in the former definition to the left side. Possibly begin working with that.
Move f to the left, so we'll have h
So
minus
minus
f.
Yeah, and then we apply negative to that, since we have negative f on the right side.
Ah, good. Okay, so you're trying to manipulate this to solve for f of a.
Correct.
Okay, before doing that, let's write down the definition of f prime of a and see if we can massage it. We want to write it in terms of h and g, but it might not be the most useful to solve for f of a first. So,
Okay.
what should we do for this?
In terms of h and g, there's a way to do this. I must remember how.
Well, forget about h and g for the moment. What can we write this as just from the definition?
This is equivalent to the limit as h goes to 0 of f of x minus f of x plus, well, f of a plus h, pardon me.
Good. F of
a plus f of a plus h.
So like this.
Oh. Right.
Is that what you said? Or did you have signs?
Swapped around, I believe. Unless that is also true, in which case interesting.
Wait, isn't this the
I'm
usual?
not remembering the definition right.
I think this is right. Yeah, I mean you look at a point a little
Yeah,
bit
that's
to the
right.
right.
Okay.
Get, okay, so we actually proved there's a couple other ways to express this. So if we trade h for x, so get rid of h. Instead of saying h goes to 0, let's write this in terms of a variable x, which is getting close to a. So in other words, change variables. So h is x minus a. If you do that, what does this limit become?
We let h equal x minus a, and we substitute h for x minus a to get that this is going to become f of x minus f of a over, and limit as h goes to 0. Oh wait, over x minus a. Limit as x goes to 0. Right.
Well, let's see. As h goes to 0, what does x go to?
X goes to a.
Yeah, so it's not the limit as x goes to 0, but the limit as x goes to a. Good. Okay, so I claim that this quotient inside the limit can be written very neatly in terms of these two functions h and g. So if I substitute in h and g, what does that limit become?
Substituting h and g, we see that this limit of h of x over, desperately trying to remember, over g of x.
Good. Okay, so this is very nice because we know h goes to 0 as x goes to a. Right? So you can just plug in x equals in here, f of a minus f of a is 0. Similarly, g goes to 0 because a minus a is 0. So we can apply L'Hopital's rule and just take the derivative of the top and bottom. And that gives us an h prime over g prime. And then using the definitions of h and g, what is this limit?
This is thinking. By definition of g, this is equal to f prime of x. Am I supposed to be into derivatives or just a number here?
These are still functions, so the derivatives.
Okay. Yeah. So f prime of x minus f prime of a.
Well, let's see, the derivative of this is 0.
They are constant. Right, okay. Now you know.
Ah, fucker.
Oh boy.
Good, so f prime upstairs, g prime?
And g prime is equal to 1.
Good. Okay, so this is just the limit as x goes to a of f prime, which is, as we started on the left side with the expression f prime. So I'm just going to rewrite this without the 1, but this is the statement now by L'Hopital's rule that the limit as x goes to a of f prime is equal to f prime at a. which is just the statement that we wanted to prove, which is the derivative is continuous, right? So the limit as x goes to a of f prime exists, and it's equal to f prime at a. So the derivative cannot have a point discontinuity, as we wanted to prove. So it all boiled down to applying L'Hopital's rule cleverly to the functions in the top and bottom of the difference quotient that defines the derivative. That's the point. Good. Thoughts on this?
I have no thoughts.
Cool beans. Okay, so just one more time. So following the hint, as you said, you let h be f of x minus f of a, g be x minus a. As I've argued that, both of these guys go to 0 as x goes to a. So apply L'Hopital to the limit of their quotient to get, I dropped a parenthesis here, to get the limit as x goes to a of h prime over g prime, which indeed, as you told me, is the limit as x goes to a of f prime. Good. So the punchline is that derivatives, under these assumptions, if they exist on an interval, derivatives cannot have point discontinuities. They can have jump discontinuities. Obviously, you can have a function who has my pen's skipping, but a very small slope, and then he has a kink and jumps to having a very steep slope. That's fine. That's a point discontinuity. So f prime would look like small positive number over here. Man, I can't draw it all. Fucking hell. Okay, well, you see what I'm trying to say. You get a small positive number derivative, big positive number derivative. So the derivative can have a jump. It can't have a point discontinuity under these assumptions. That's, I think we use that result later in the stuff on infinite sequences and series, but we'll see. Good. Okay, enough on L'Hopital. So now just some more kind of application type problems, crunchier problems involving throwing balls and things and seeing how they move. So thoughts or questions before moving on?
Bullets. Necessary.
Very important. Okay, so what did we speak about last time?
Are you recording?
I think so. Yes, still recording. Good.
Good, okay. Oh, I suddenly remembered that.
You've been very diligent in checking for me. I appreciate this. Okay, so the last time we spoke about physics, I think I, gave this example about a particle moving around with some cubic for his position x of t, and we use this to understand the definitions of velocity and acceleration, which are just the first and second time derivatives of the position function, right? So x is the distance from some origin to a particle, and then we define v as dx dt and a as v dot or d squared x dt squared. And then I argued we should stop at accelerations because empirically all of the physical laws of nature, or at least all the ones I'm aware of, are second order in time derivatives. So you have, f equals ma, for instance, where a is d squared x dt squared, so this only has two time derivatives, second order. That was the last thing we said, and now we should try to use this. So let's just write down some Newton's second law equations for interesting systems and see if we can anti-differentiate. So go backwards to solve and get x of t. Because we want to know, that at the end of the day, that's the answer we want. We want to know where is the thing at each point in time? What is its position x of t? So let's do that in a nice simple example of just a gravitational field. So I'll work this one out for you. So suppose I stand at the top of a building and I drop some object, a penny or a ball or a bullet or something, and I drop it from this initial height h. So it starts from h. There's a constant gravitational force directed downwards. So as I've written f, I'll put the y to emphasize that this is kind of in the vertical y direction, if you will. So f sub y is supposed to be minus mg, the mass of the object, times this gravitational constant. So just copying down the Newton's second law that I wrote on the previous slide with y instead of x, I set this force equal to mass times the second derivative of y, the acceleration, so to speak. So this is Newton's second law, and then canceling the masses from both sides, we say this is just the statement that if you take two time derivatives of y, you get this constant negative g. Well, we know how to anti-differentiate, right? So if you take two derivatives and you get a constant, I can undo one of those, so that means y dot, one derivative, is going to be minus gt, possibly plus a constant v0, by 0 I mean at time 0, y. But I'm saying we drop this with 0 initial velocity, so actually this thing goes away. This thing's nothing. And then we can undo one more derivative, because by kind of like the backwards power rule, you ask what function should I write down, so if I take a time derivative, I get minus gt. Well, it's pretty obvious. It should be minus a half gt squared, because when I take the derivative of this, I pull a 2 down, it kills the half, and I'm left with minus gt. Again, this could be possibly plus a constant, because the derivative is going to genocide that constant, and you would not see it in the second line. And we know that at time 0, this guy has height h. So when I plug in time 0, this first term goes away, and I know the answer should be h, so I should add the constant h to make that work, to match the initial condition, as we call it. So whatever, anyway, so that's, not rocket science, but this is the trajectory, the position of the object as a function of time if I drop it from height h in a constant gravitational field. Good. Okay. Thoughts?
One could say that this is the opposite of
The opposite of what? Sorry.
rocket science.
Yeah, it's true. It's not going up. It's something going down. It's very poorly designed rocket science. If your rocket, rather than leaving the atmosphere, just drops and crashes, then you are not a very good rocket scientist.
Unless there's positive gravity.
Ooh, that would be interesting. What if gravity were repulsive? The Earth would fling you away from it. Okay, so let's use that. I will recopy the equation for reference, but it was, I think, y is h minus a half gt squared. So let's put some numbers in. I drop a penny off a building which has a height of 100 meters, and we're just getting a rough estimate. So numerically, this g constant is 9.8 meters per second squared. To make the numbers nice, let's just call that 10. And I'll ask you, how should I calculate the time, so the time t, which it takes for the penny to hit the ground? So by the ground, I mean height 0, y equals 0. What do I do?
I believe we can start by inserting known minus 5 meters per second squared. I said 5 because...
Good, so you're saying y is, what is it, 100 meters minus, you said 5 for this? Because that's a half times 10?
Correct.
So that should be units 5 meters per second squared, right? Times t squared?
Right.
Good, okay, then what?
Thinking. Oh yes, y, as you wrote down, y equals where 0 is.
Good, that's the ground.
Something, but we did say that. Right, 0. And we can start by just subtracting 100 meters from each side.
Good, so...
Off.
So minus 5 meters per second squared t squared is minus 100 meters. Good.
And then we can divide each side by negative 5 meters squared.
Okay, so t squared, let's see, 100 over 5 I think is 20. Meters cancel, 1 over second squared is second squared, so good, the units seem to be in good shape. Then what?
I believe we can take the square root of each side. Of course, we don't need to worry about negative t.
Yeah, the negative root's fake. Just the positive one.
So, 2 root 5 seconds.
Good. 2 root 5 seconds. Good, so indeed that is correct. I now realize too late that when I wrote this slide, I got to the end of the problem and then changed the numbers because I didn't want it to be a square root. So I went back and changed the number at the top from 100 to 125 so that it would work out nicer. But I changed it on the solution and not on the challenge. So as you see, when I advance to the next slide, I look a little schizophrenic because now I seem to have changed the height of the building to 125 meters, which is unfortunate. But anyway, what we did before was correct. But if it were instead 125, as you said, we should replace this by 5. So this is a 5. Then it works out very nicely because 125 over 5 is 25, and the square root of 25 is a nice number, 5, without the square roots. Okay, well that's on me, but what we did was correct. And indeed, the negative root, whenever you take square roots in an equation, you should check whether one of the roots is fake, if it's spurious. But in this case, indeed, before it took, 2 root 5 seconds to drop from 100 meters, but here it takes 5 seconds to drop from 125 meters. Good. Okay, so
what is the approximate value of root 5? I'm curious how much that difference is. I don't know.
You're asking what's the approximate value of root 5?
I keep muting myself, and sometimes...
Yeah, you keep cutting out mid-sentence. I heard up to sometimes, and then I heard silence.
Yeah, I don't know why it keeps happening. It happens when I talk for too long.
I don't think I've ever had the thought that you have talked for too long, but okay.
Discord thinks so.
Discord is rude. Was this the question? What is root 5 approximately?
About. Just because curiosity.
Let's see. So this is square root of 4 plus 1, which is approximately root 4 plus, let's see, we know the square root of x is, how should I say this? Better way to say it. So if f of x is square root of x, then f at a is approximately, let's see, sorry, how should I do this? This is not how I want to say this. A plus a number, how about this? F of a plus h. So a plus h should be approximately square root of a plus the derivative of the square root, which is 1 over 2 times the square root at a times the distance h. So square root of 5, which is root 4 plus 1, should be roughly root 4 plus 1 over 2 root 4 times 1. So if I haven't made any arithmetic errors, this thing should be roughly 2 plus 1/4, or approximately 2.25. It should probably be good to about 1 decimal.
Lovely. I don't know why I was curious.
I think it's a good question. Now I'm curious how good that is. Let's see what Google says. Squirt 5. Now you see how long it takes my computer to register. He's thinking.
There it goes.
Come on. Squirt 5. Come on. What's it going to be?
Stuff appeared.
2.236. Not bad. So it rounds to 2.24. So we're off by roughly 0.01. It's pretty good. Pretty good for a first order tangent line approximation. But good. Good question. Other questions or thoughts?
I have no questions or thoughts.
Nice. Okay. Alright, let's make it a little more interesting. I will challenge you, what changes in the derivation that we just did, those 2 steps of anti-differentiation, if now I say I throw the penny? I don't tell you whether I throw it up or down, right? So v0y could be positive or negative. If I throw it up, it's positive. If I throw it down, it's negative. But, this should be h, sorry. Y at times 0 is still h, the height of the building. So what changes? If I throw it, what is the penny's new height, y of t, as a function of time?
That's something to recall the equation we found.
This is where we started from, right?
Did your pen cut out?
I think it's still working. Right. Can you see? Is it lagging?
Wait, there's just a G. Okay.
Should be y double dots minus g, right? That's where we started from. Then we tried to anti-differentiate.
Okay, so let's see. This is going to be -1/2 G. No, we need to add a variable. So negative G of some variable.
Well, hold on. G's a constant. G's just a number, right? Maybe I should write it to remind you that the variable is t. Right, G's a constant. These are functions of t. So this is d squared y dt squared. And we're trying to write dy dt. So what should I write down on the right side here? So if I took the derivative with respect to t, assuming g is a constant, I would get minus g.
Negative G of t?
Or negative g times t, right? Yeah.
Well, yeah.
Yeah, g's not a function. G's just a number.
Right.
It's like 10. Right. Good. So yeah, if I took the derivative, damn it, I took the derivative of this with respect to t, I would get minus g back. However, I also have the freedom to add a constant, because the derivative would murder the constant. So if I would like it,
where we want to add things, because I believe that currently in the velocity point.
Yeah, so what should I write? How should I incorporate the velocity here?
We simply add on v sub 0 y.
Good. Yeah, so this works. If I take the derivative, I get this back, and it satisfies the property that y dot at time 0 should be v0 y. Good, so it satisfies the initial condition. Now, let's do one more step. If I anti-differentiate again, using the second initial condition, y of 0 is supposed to be h. What do I get here?
This is going to be -1/2 g times t squared plus v sub 0 y. I think. Oh, did my stuff cut out again? Times t.
There we go. Good. And then I could still add one more constant. Which constant should I add so that this is true?
Of course, it registered until I said the thing. Oh my god, it keeps cutting out. H.
Good.
Jesus.
You must feel like I'm being very rude, because from your perspective it must sound like I'm interrupting you a lot, because I can't hear you talking, so it sounds like I'm talking over you, but I assure you, from my end, it does not sound like that, so I apologize.
But your own voice comes across like it plays through my speakers, and it
you cut out again. I heard up to it plays through my speakers.
Are you serious? I'm turning on push.
Kill it.
Oh my god, that timing. I said push to talk, and it just...
Lost you again.
Finally. There we go.
Is it just push to talk, or should we try restarting the call or something?
I am back to using push to talk because it doesn't cut off mid-sentence.
Okay, good.
Maybe it needs to talk louder.
Yeah, I think you should just scream, because I think it has a volume threshold, which is unfortunate because you're kind of soft-spoken. But, okay, good.
Anyways, that is
correct.
Exactly the function. Yeah.
Okay, so this is nice. Now we know both with an initial velocity and an initial position, I can tell you exactly where this thing's going to be at each point in time. So this is very nice. I mean, it's not super complicated. We just had to, do some dividing by 2 is the only hard step here, is, going up and doing this backward power rule, so this isn't bad. But the nice thing about this is now this allows us to describe, with one extra step, motion in 2 dimensions. So everything we've said so far has been just one dimension, by which I mean there's only one coordinate we care about, right? So I write down the height y of t. So you could ask what happens if I throw something now. Damn it. If I throw something and now I care not just about its height as a function of time, I care about both where it is in x and where it is in y. Two-dimensional. So let's tackle that next. What will that look like? Well, first, just repeating the solution that we just got. Everything was fine, so that's good. Let's talk about two dimensions now. So I've actually written this as a fairly long scaffolded problem in CD4, so you'll just go through all of these steps and repeat them. But I want to get you started by kind of giving you the idea and working through some of the calculation. So let's describe the motion of a projectile. So say you fire a bullet or throw an object, like, I don't know, you're throwing a javelin or some shit, doing track and fields. And anyway, for convenience, we will assume that the object starts at the origin. So at time 0, it's at the origin. And you throw it with an initial velocity, which is kind of the faded arrow here. This initial velocity, v sub 0, is kind of makes an angle theta with the x-axis. So the reason it's shaded is because we immediately want to decompose that velocity. We want to break it up into its x and y components. So by trigonometry, you can see pretty easily that if this guy, this v0, is an arrow which is pointing up like this with angle alpha, we can split it up into the x and y pieces of the velocity, right? So the horizontal component of this arrow is simply v0x equals v0, the length of the hypotenuse, if you will, times cosine of the throwing angle alpha. So that's fine. v0y is similarly v0 times the sine of this throwing angle alpha. So now we know the initial velocities, we know the initial position, right? X at time 0 is 0, which is the same as y at time 0, because this guy starts at the origin. So now we can just solve this problem in the same way we did throwing the penny, except with two copies of that problem. The reason that there are two copies is because we get decoupled equations. Decoupling means we can write these two second law equations separately and solve them independently without, using the results of one of them in the other equation. Sometimes, the y equation depends on x, and the x equation depends on y, so they're coupled, and you can't solve them separately because they both talk to each other, so to speak. But in this case, they decouple, so it's actually very easy. And we get two equations. The two equations are, very similar to the ones that we just solved. They are first that the acceleration in the x direction is 0. That's because we're just assuming that gravity points down. So if gravity points purely downwards, there's no force horizontal, right? If there were wind or something pushing this guy, you would have a force in x, but we're assuming that's not the case. The second equation is the same thing we did with the penny, that the force in the y direction is just a uniform gravitational force downwards, right? So a minus mg pointing down. Those are our two equations. Now we're going to solve these two subject to these initial conditions in precisely the same way we did for the penny. So let's do that. Okay, so repeating what I said a moment ago, the initial y velocity is v naught sine theta, the initial x velocity is v naught cos theta, and then, I've just cited the answers here, but it's pretty easy to see just by anti-differentiating. Let's start with x double dot equals 0. Well, we have to write down a function whose derivative is 0, so that has to be a constant. So the constant which agrees with the initial condition, which is v naught cos theta times 0, is simply that this guy is the constant function theta alpha, v naught cos alpha. And then you anti-differentiate again. I need to write down a function, so when I take the time derivative, I get this guy, and that's simply v naught cos alpha t. I could add an initial, point x0, but he starts at the origin, so that thing is 0. That's the first one. Same thing as the penny, actually, same exact argument. If y double dot is minus g, then y dot supposed to be minus gt plus the initial y velocity, which is v naught sine alpha. And again, anti-differentiating y is going to be minus a half gt squared plus v naught sine alpha t. Same stuff. So that gives us those two positions. V naught cos alpha t minus a half gt squared plus v naught sine alpha t. So that tells us where in both x and y our bullet or javelin or whatever is at each point in time. Okay, good. So let's do a challenge now. I've just copied those two equations from the previous slide. Here's the x and y. Now, the apex is the highest point on the trajectory. So here's the apex. I will ask you, now that we know where this guy is in x and y at each point in time, how do we find the time at which it reaches the apex? So at what time t does the projectile reach the apex of its trajectory? What should we do?
Where the derivative equals 0 of y of t.
Good, okay. So what's the derivative y dot? What should I write?
Y dot is equal to, thinking, negative g of t plus 0.
This guy is a t, right?
Right. Plus v sub 0 sine alpha.
Good. Okay, so indeed, as you say, this guy, I mean, it's it's a place where the velocity in y is 0. He's reached the top. So let's solve this for t, and then what value of t do I get at the apex?
So we can subtract v sub 0 sine alpha from each side and then divide by negative g.
Good. What do you get?
Equals v sub 0 sine alpha over negative g, or negative over just g.
Yeah, g. Negatives cancel. Good. Okay, so quick sanity check. I mean, you should always, when you're doing physics, you should always get in the habit of stopping and thinking about units. If your units are fucked, then your answer's fucked. So v is a velocity. This is in units of meters per second. G, I told you a couple slides ago, has units of meters per second squared. Sine alpha, well, sine is dimensionless, right? Sine is just a number, like 1. It has no units. So all we have to do is take the ratio of these two. But, I mean, you should just treat these units as letters in algebra, so you can manipulate them in the same way. So to do that, this is the same. Dividing two fractions is the same as multiplying by the reciprocal. So this is meters per second times the reciprocal of the bottom, which is seconds squared per meter. Meters cancel. One factor of seconds cancel. We get seconds. So our answer for time has units of seconds, which is pretty good, because where I come from, we measure time in seconds. So that's comforting. And indeed, this is the correct answer. This is so important in physics that it gets a fancy name called dimensional analysis. I think I've said this name before, but just to remind you, dimensional analysis. It's a very fancy name for a very simple observation that you should check to make sure your units work. Good, okay. Other thoughts on this challenge?
Does physics demand a fancy name for everything?
Kind of, yeah. I don't really like it. It sounds very, I don't know, arrogant or pompous to give fancy sounding names to things, but it's a common theme, unfortunately. Good. Okay, let's do another challenge. Well, first making sure we got the right answer. I think this is what we wrote, yeah. T at the apex is v naught sine alpha over g. And just one observation, which will be helpful to you when you do the challenge, the problem on this in the CD4. As you can probably just tell intuitively by geometrical intuition, that this guy is symmetric about reflection about the apex. Again, whenever, I mean, symmetry means invariance under a change. So when I say it's symmetric, what is the invariance and what is the change? The change is you take every point and reflect it, which means you replace its x-coordinate by its the corresponding x-coordinate, which is the same distance from this vertical line on the other side. So you replace every point by its mirror image about this line, and the trajectory stays the same. As a consequence of this, it's pretty obvious that this t ground, where it hits the ground, has to be twice t apex, right? Because by symmetry, if I reflect this whole guy but the center and it stays the same, then that means you have to spend as much time on this side as you do on this side, otherwise it wouldn't be symmetric. So that means t ground has to be twice t apex. So in the consolidation document, you will do a few more calculations where, well, you'll write down this answer to find the time at which it hits the ground, then you'll find x at t ground, so you'll find the range, so to speak. Not range in the sense of domain and range, but the range is in how far your bullet goes, right? So this is just the total distance the projectile travels while it's in the air. And then you will maximize this. So the nice thing about calculus is we learned how to find the maxima and minima of functions. So you will find the maximum range of a projectile over the angle alpha, which is simply the question, if I want to throw my javelin and have it go as far as possible, at what angle with the ground should I throw it? And, I mean, you could probably guess the answer. You should throw it at 45 degrees if you want to maximize the range. But it's good to actually prove that. It's not actually true in real life because there's air resistance. We're dropping air resistance in this problem, which makes the problem more interesting to solve with air resistance. But if you assume no air resistance, so you're just throwing this in a vacuum, then the answer is 45 degrees, which you will prove. But
Question.
Good question.
Is the graph we're looking at there technically three-dimensional?
Yeah, if you like, you could think of a z-axis coming out of the plane of the screen. But there's nothing going on in z, right? We're assuming this guy just kind of sits at a fixed slice in z, like z equals 0 or something. You could do the same problem and say I'm going to throw it with v naught that has 3 components, right? So there's a v naught x, a v naught y, and a v naught z. And you could solve it with that third dimension, but it's basically the same story. You just get one more equation, and the z acts like the x, so it's not really much new.
I was curious because I feel like time should be graphed somewhere here.
Oh, I see. Yeah, because you're used to. Yeah, I should have emphasized this. The graphs we were drawing before, when we talked about velocity, had a different y-axis than this one. So this is important not to confuse them. If you draw a position versus time graph, actually, sorry, in physics we usually put time on the y-axis. Didn't I do it last time? I think it was x here and time here. Sorry. This is what I showed you last time. So when we draw a graph like this is just saying I'm finding where this guy is as a function of time. So at time, different color, at time 0, this guy's, I don't know, 1 meter away from the origin, and maybe over here at time is 10 seconds or something. This guy is more, maybe 2 meters away from the origin. So this is one kind of graph. It shows where you are as a function of time. If this is the type of graph you are looking at, then the derivative, the tangent line slope, is the velocity, right? So this is x dot, the tangent line slope. So this is what we looked at last time. This type of graph is totally different from the graph I've drawn here. The graph I've drawn here, repeating it, is y and x. Time is conspicuously absent. There is no time. I'm showing you the y, the vertical coordinate is the position above the Earth's surface. The horizontal axis is the range, the distance the projectile has moved. There's no mention of time. So it is no longer true that the tangent line slope here has anything to do with the derivative. This tangent line slope is dy dx, which has nothing to do with the velocity. It's not y dot, it's not x dot, it's just it's a trajectory, not a velocity. So it's important not to confuse these. Coming back finally, that was a rambling answer. Coming back to your question, should there be a third axis for time that shows us where this guy is moving around? Yes. So you could, if you like, describe this as a txy plot. So at each time, there's one value of x and one value of y. This is harder to visualize, I think. I prefer to look at two-dimensional plots and just think of time as kind of like a hidden parameter. Like for each of these points, maybe here's t is 1 second, here t is 2 seconds, whatever. So time is secretly here, it's hidden. Each of these points has a time associated with it. It's just not plotted explicitly. I think that's easier personally because two-dimensional plots are easier than three-dimensional plots for my brain. But it's a very good question. Yeah, there should really be a third degree of freedom or third variable here. Good. Other thoughts?
I'm suddenly curious if I can generate graphs in Fusion 360.
Ooh, I know you can in Mathematica. I don't know if, Desmos or whatever you use can. Good, good. We'll have more to say about this in some later chapter when we do parametric plots. This is a parametric plot, which just means it depends on a parameter, which happens to be time. But whatever, more on that later. Okay, I think this is the last thing. You may have noticed that it certainly seems like the graph of where the projectile is in the xy plane looks like a parabola. But we haven't actually proven that because what we have written down are two functions x of t and y of t. And to prove that this is a parabola, we have to write down y as a function of x, which is different from these, right? So I will challenge you. Oh.
Can you substitute x for t?
Yeah, exactly. Good. So, so do that. So how would I substitute x for t, which is to say solve this equation for x and plug it in, or sorry, for t and plug it in here? What should I do?
Oh, okay. I need to do that somehow.
Yeah. Well, first, what's this? So if I solve this for t, what do I get?
Solving that for t gets you v sub 0 of cos alpha. Not of, just v sub 0 cos alpha.
Where's the x though?
But basic algebra. Wait, what?
So we're solving this for t as a function of x, right?
Oh. Now I understand the question. X of t divided by v sub 0 cos alpha?
Good, yeah. So just divide both sides by v naught cos alpha, and you get this guy. Okay, good. This is how you eliminate variables, right? If you have two equations, you solve one equation for the variable in question, and then you plug that into the second equation. So let's do that now. So I'm going to rewrite y of t. What do I get on the right side of this equation when I plug in for t this expression involving x?
So we're simply substituting t for that thing?
Yeah, good.
And just negative 1/2 g. Begin quantity xt over v sub 0 cos alpha quantity squared plus v sub 0 sine alpha.
Yeah, good. So the second term is unchanged. And I'm going to rewrite this in a somewhat more suggestive way to make it clear that it's a parabola. So I'm going to pull out the x squared and write this as a minus 1/2 g times 1 over, I'm keeping this v naught squared cos squared alpha, so that guy's all in parens, times the x squared. There's no term proportional to x, so I'll just put in a 0x. And then this guy's a constant as far as x is concerned, right? This guy doesn't depend on x at all. So I'll put it in parens just to emphasize. So now when we look at the structure of this equation, this is, well, from the point of view of x, this guy's a constant. 0 is certainly a constant. v naught sine alpha is a constant. So this is just y equals ax squared plus bx plus c for a particular, wonky choice of the constants a, b, and c. So indeed, this graph, the graph traced out by the projectile as you throw it or shoot it, is a parabola in xy space. So just rewriting that a little more cleanly, as you say, if I solve for t, I get x over v naught cos alpha, plug it in for y, plug that in for t in the y of t, I mean, and we get this junk, square out the x squared, and collect these guys into this constant. And indeed we get the parabola y, sorry, you should put the argument of your function, you should put in there what it actually depends on. So I shouldn't have written that as y of t, I should write it as y of x, because we've eliminated t. Now it depends on x. But anyway, so now y of x, y is a function of x, not of t, is this ax squared plus bx plus c junk. So that's the punchline. So projectile motion is indeed a parabola. Good. So again, you'll write out this proof on CD4. I'll probably post that maybe tomorrow. I'll post more problems, and then you can, try catching up on the other ones, and then work on this.
A quick side note: I've literally been waiting my entire life to be able to understand this.
Wait, why? Because you like shooting things?
No.
Why are you? What's especially interesting about this?
This is, I don't know. It's just something that I wanted to be able to understand for a long time, given an angle and a speed, do things.
Yes. I felt the same way when I learned this, because it seems like a very natural question, right? That any 6-year-old could ask, right? If I throw my fucking toy, what happens, right? I mean, it's so natural. I think it's an embarrassment that the full correct answer to that question is usually never discussed in high school. Even when I took honors physics with Mr. Conrad, he showed us, I guess, this equation, this answer, and then gave us questions on a test, which were just like plugging in numbers, like if v naught is 5 meters per second and alpha, I don't know, alpha's 30 degrees, write these down, plug it in, and write down numbers. But I find that very unsatisfying, because more interesting, I think, than just plugging in numbers is understanding how it works, why it is what it is. And now hopefully you do see that, because this all just followed fairly simply from undoing some derivatives. And from my perspective, the reason to understand it at that level rather than in the plugging in numbers level is because now assume, some ugly fucker comes along and says, well, I'm going to change the problem. And he says, okay, so now I fire this with angle theta, but also I'm going to tilt the whole problem. So actually, you're standing on a hill and you throw this guy, maybe you throw this guy at angle alpha, but there's a second angle, which is the angle of the hill, which is phi. Now what happens? Now it's different. You're throwing it down a hill. Should I still throw it at 45 degrees? What is the maximum angle? Or sorry, what is the angle which maximizes the range if you're throwing off a hill? So this was on the first problem set of the first physics course I ever took at MIT, which was 8012. And you can ask, okay, well, what if I make the problem even harder? Maybe now I add air resistance. So now there's air resistance. So there's some drag, F drag, a second force. So you complicate it. And if you know how to think about the problem and how it works, then, okay, maybe these changes to the problem are difficult, but you still know generally what you should do to solve the problem subject to those changes. However, if you just memorize how to plug in numbers to these formulas, when someone comes along and changes the problem, you're totally stumped, because you never learned how to think about the problem, you only learned how to plug in numbers. And the sad thing is, in the real world, in any job, or in academia, or in a lab, or if you're a professional physicist or chemist, you're never going to be solving canned problems that just involve plugging in numbers. You're always going to be solving messy, complicated things where no one knows the answer, and it's more important to be able to think deeply about what you should do to make those modifications rather than just regurgitating. But anyway, sorry. You're getting an earful of my rant, but you've heard this rant or a similar rant probably dozens of times now, so I will shut up.
It never gets old.
Good. Okay, other thoughts on projectile motion?
Wait, what did you say?
Other thoughts on, did I
Oh,
say?
I thought you were saying project something,
Oh,
and you were saying that, but I thought you were saying some kind of. I don't know. It almost sounded like Project Revolution.
no, fuck that shit. I will not entertain any questions on Project Revolution, but I will entertain questions